All right, welcome back to the deep dive. Today we're diving into the fundamentals, like really fundamental stuff.
Oh, yeah, we're talking work, energy, and power.
Exactly. Mechanics, how things move, why they move,
Yeah.
you know, all that good stuff.
So this one might seem a bit dry at first, but trust me, it's the bedrock. Like all of physics, all these crazy phenomena we talk about, it all goes back to energy
Yeah,
and how it changes.
totally. And today we're going to zero in on kinetic energy. That's the energy of motion, how it's tied to work. And then, of course, power, which is just how quickly that work gets done.
We're going to really unpack these concepts. And to do that, we'll be drawing on some stuff we've talked about before, like remember scalar products
Yeah.
and force components, constant acceleration, Newton's laws, all those come into play.
Okay, let's start with work. I think the first thing we got to do is clear up what work actually means in physics. It's a bit different from how we use it in everyday life.
Right. You say I had a hard day at work, but like in physics, it's way more specific.
It's not just about effort, right?
Exactly. In physics, for work to be done, a force has to act on something and actually make it move. So you could be pushing on, I don't know, a huge boulder with all your might. But if that boulder doesn't budge,
No work done.
no work done, at least not on the boulder. You might feel tired, but physics says not work.
Okay, so let's say we are actually moving something. What's the equation?
So if you've got a constant force and it's pushing or pulling something in the same direction as the movement,
Yeah.
work, or W, is just the force, F times the displacement, which we call S.
Okay, simple enough.
So the bigger the force or the further it moves, the more work is done. Makes
Okay.
sense.
Makes sense. And what units are we using here?
The unit for work, and actually for any type of energy, is the joule,
Joule.
which we write as J. And a joule is the same as a Newton meter, which we write N.M.
Gotcha. Now things get a little trickier when the force and the movement aren't in the same direction.
Yeah, like imagine pushing a box across the floor, but your force is kind of angled downwards. Not all of that force is actually moving the box forward.
Right, some of it's pushing it down.
Exactly. So then the formula for work gets a little fancy. W equals F times S times the cosine of phi.
Phi.
Yeah, phi. It's the angle between the force and the displacement. Basically, this cosine factor is there to account for how much of the force is actually contributing to the motion.
I see. So if the angle's really big, meaning the force is almost perpendicular to the movement.
Then the cosine gets really small, meaning very little work is being done.
And that's where the scalar product comes in, right?
Bingo. You can express work as the dot product of the force vector and the displacement vector. W equals F dot SS. Really elegant, takes care of both the magnitudes of the force and displacement and that pesky angle all in one go.
Neat. Okay, but how do we know if work is like adding energy to something or taking it away?
Think about the angle again. If the force has even a tiny bit pointing in the same direction as the motion, meaning phi is less than 90 degrees, the cosine is positive, so work is positive, like pushing a swing to make it go higher.
You're adding energy to the swing.
You got it. Now, if the force has a component working against the motion, phi is greater than 90 degrees.
Yeah, like friction.
Exactly. Cosine's negative, work's negative. You're essentially taking energy away.
Okay. Then there's zero work. When does that happen?
Well, the obvious case is if there's no displacement, no movement, no work, even if there's a huge force.
Right.
But you can also have zero work if the force is perfectly perpendicular to the motion. Phi is 90 degrees, cosine of 90 is 0, boom, no work.
Okay, so let's see some examples of that. Imagine you're holding like a really heavy weight, just holding it still.
You're definitely using force, fighting gravity, but the weight's not moving up or down. No displacement, no work, at least on the weight itself.
Right. What about carrying that weight across the room, like at a constant speed?
Okay, so you're exerting an upward force to support it, but the movement is horizontal, perpendicular. So again, no work done by that upward force.
Interesting. Okay, what else?
The normal force, that's the force a surface exerts on something resting on it.
Right.
It always acts perpendicular to the surface. So if something's sliding across a table, that normal force does no work. It's not involved in the horizontal motion.
Got it.
And then there's uniform circular motion, like a ball on a string swinging around in a perfect circle. The tension in the string is always pulling the ball towards the center, but the ball's actual movement is always tangent to the circle, so at a right angle.
Meaning the tension isn't changing the ball's speed, just its direction.
Precisely. Zero work.
Okay, so what if we've got multiple forces acting on something? How do we find the total work?
Two ways. You can calculate the work done by each force separately, accounting for those angles. and just add them up.
Okay.
Or you find the net force, that's the overall force, the vector sum of all the forces, and then calculate the work done by that net force. Both ways get you the same answer.
Makes sense. All right, let's talk about kinetic energy. That's the energy of motion, right?
Yes. And the formula is beautifully simple. K equals 1/2 times the mass, m times the speed, v squared. K equals 12 milliV of A.
So it depends on how massive something is and how fast it's going?
Exactly. And notice that the speed is squared. So if you double the speed, you actually quadruple the kinetic energy.
Wow.
Also, remember, kinetic energy is a scalar. It has a size, a magnitude, but no direction.
Okay.
And since mass can't be negative and speed squared is always positive, kinetic energy is always positive or zero.
Gotcha. And what are the units?
Joules, same as work.
Okay, so now we get to this really important idea. The work energy theorem.
This is where it all comes together. This theorem says that the total work done on something is equal to the change in its kinetic energy. Simple, but super powerful.
So if you know the total work done,
Boom, you know how the object's kinetic energy changed?
and vice versa.
Exactly, and that means you know how its speed changed. You don't even have to mess with acceleration and all those kinematic equations. It's a shortcut, a direct link between forces and changes in motion.
So it's like W total equals K2 minus K1.
Yes, or W total equals delta K. And that expands to 1/2 mv2 squared minus 1/2 mv1 squared, where v1 is the initial speed and v2 is the final speed.
Nice. Okay, does this theorem work all the time?
Pretty much. It's valid in inertial frames of reference, which means non-accelerating viewpoints, and it even works when the forces aren't constant, super versatile.
So this is like a fundamental truth in physics.
Definitely. And you can even interpret kinetic energy itself using this theorem. The kinetic energy of something is the total work that had to be done to get it from rest to its current speed.
So if it starts at rest, meaning V1 is 0,
Yeah.
the total work done equals its final kinetic energy.
Exactly. All that work went into making it move that fast.
And you can think of it the other way too, right?
Absolutely. The kinetic energy is also the total work that something can do while coming to rest. Like, think of a bowling ball. It has kinetic energy, and as it hits the pins, it slows down, hopefully to a stop, right? In that process, it does work on the pins, making them fly around. That's its kinetic energy being transferred.
That makes sense. Okay, so what happens when the forces aren't constant? Like they're changing as the object moves?
Good question. That's where we need a little calculus. Let's say we've got something moving along a straight line, and the force acting on it, Fx, is changing depending on the position, x.
Okay.
The work done by this varying force as the object moves from by 1 to by 2 is given by an integral.
An integral.
Yeah, it's basically a way to add up all those tiny bits of work done as the force changes over that distance.
Okay, I vaguely remember integrals.
So W equals the integral from by 1 to by 2 of Fx with respect to x. And this integral actually has a cool visual meaning. It's the area under the curve of a force versus position graph.
Oh, I see. So you plot the force on the y-axis and the position on the x-axis.
Exactly. And the area under that curve between by 1 and by 2, that's your work done.
Yeah.
And a really important example of this is a spring. The force it exerts changes as you stretch or compress it.
Right.
This is Hooke's law. It says the force, Fx, is proportional to how much you've stretched or compressed it, which we call x. So Fx equals Kx.
And K is that spring constant thing.
Yep, the spring constant. It tells you how stiff the spring is. A bigger K means a stiffer spring, harder to stretch.
Gotcha.
So if you use this Hooke's law equation in the work integral, you can find the work done to stretch or compress a spring by a distance x.
And what's that?
Turns out it's W equals 1/2 K times x squared.
Okay.
And if the spring is already stretched a bit, say by 1, and you stretch it further to by 2,
Yeah.
the work done is 1/2 K by 2 squared minus 1/2 K by 1 squared.
Interesting. So that covers forces that change along a straight line.
Yeah.
What about curved paths?
Things get even more fun then. We have to use something called a line integral. Basically, instead of just adding up work along a straight line, we're adding it up along the curve.
So it's like we're chopping the curve into tiny, tiny segments.
Exactly. Each segment has a tiny displacement vector, dl. And the work done by the force along that tiny segment is the dot product of the force and dl. Then we add up all those tiny works using the integral.
I see.
So formally, it's the integral from point 1 to point 2 of F dot dl. And remember, that dot product takes care of the angle between the force and the displacement at every point along the curve.
Okay, so we're still basically finding the component of the force that's pushing along the path.
Absolutely. And you can also write this line integral in other ways, like the integral of F cosine phi dl, where phi is that angle, or the integral of F parallel dl, where F parallel is the component of the force parallel to the path.
So it's all about how much of the force is actually contributing to the motion, even if the path is all curvy.
Exactly.
And the work energy theorem, does it still hold true in these crazy situations?
You bet. That's the beauty of it. As long as you correctly calculate the total work done, it always equals the change in kinetic energy, no matter how complicated the force is or the path.
So it's like a universal truth.
Pretty much, yeah. It's a fundamental principle in physics. It just works.
Okay, let's move on to power. What exactly is power in physics?
It's simply how quickly work is being done, the rate at which work is done. It's not just about how much work is done, but how fast. And it's also a scalar, like work and kinetic energy.
So, like, a powerful engine can do a lot of work very quickly.
Exactly.
Okay, so what's the formula for power?
Well, we've got average power, which is just the total work done, delta W, divided by the time it took, delta T. So PAV equals delta W over delta T.
Okay.
But then we have instantaneous power. That's the power at a specific moment. It's like the limit of the average power as the time interval gets super tiny. Technically, it's the derivative of work with respect to time.
Ah, calculus again.
Yep. So P equals dW dt. That gives you the precise power at any instant.
Okay, and what units do we use for power?
The SI unit is the watt, which we write as W. 1 watt is 1 joule of work done per second. So if you're doing 1 joule of work every second, your power output is 1 watt.
Makes sense.
And you might have heard of horsepower, especially when talking about engines.
Yeah.
It's another unit of power. Not an SI unit, but still common. 1 horsepower is about 746 watts.
Okay, so like a 200 horsepower engine is putting out about 149,200 watts.
Yep, something like that.
Wow, that's a lot of watts.
It is.
Okay, so is there a way to express power in terms of force and velocity? Like, those seem easier to measure sometimes.
You're in luck. Power is the rate of doing work, and work is force times displacement. So we can write power as the dot product of the force, F, and the velocity, Vp equals F dot uv, which is also F times V times cosine phi, where phi is the angle between them. Or you can think of it as the component of the force in the direction of motion, F parallel times the speed.
So if you apply a bigger force, or if the object is moving faster, the power goes up.
Exactly. Like, think of a car engine. It has to produce enough power to overcome air resistance and friction and keep the car moving at a certain speed. The faster you want to go, or the steeper the hill you're climbing, the more power you need.
Okay, I think we've covered a lot of ground here.
We have. We started by defining work and saw how it's different from just effort.
Right. We talked about how to calculate it, even when the forces are changing or the path is curvy.
And then we dove into kinetic energy, how it's related to motion and how it changes based on the work done on an object.
That work energy theorem is a pretty big deal.
For sure. It connects forces and motion in a super direct way, and it works all the time, which is awesome.
And finally, we tackled power, how quickly work is done. We talked about watts and horsepower, and how power is related to force and velocity.
We even touched on some calculus with integrals and derivatives, but hopefully we didn't get too bogged down in the math. The main takeaway is that these concepts, work, kinetic energy, and power, they're all connected, and they're essential for understanding how the world works.
Definitely. So to recap, we looked at the definitions, the formulas, gave examples, and really tried to understand how everything fits together.
We talked about joules, watts, scalar products, the whole shebang.
So yeah, I think we've pretty much covered everything from the chapter, all the main concepts and relationships.
Agreed. We aimed for a comprehensive overview, a deep dive into the core ideas of work, kinetic energy, and power in mechanics. Hopefully it all makes sense.
And as you go about your day, think about these concepts. Like when you lift something or throw a ball or drive a car, work energy and power are at play everywhere.
Absolutely.
And understanding them is the key to unlocking so much more in physics. These ideas are just the beginning. There's a whole universe of amazing phenomena out there waiting to be explored, all built on these fundamental concepts. Thanks for joining us on the Deep Dive.
See you next time.